My name is Pedro Toledo. I'm PhD student from Polytechnic Torino, Italy, as well as from Federal University of Rio Grande do Sul. And I'm going to present a paper called a 300mV-Supply 144 nanowatts power 0.03 mm² area 0.2 power efficiency factor digital-based biomedical signal amplifier 180nm CMOS technology. My advisors are Paulo Crovetti and Hamilton Klima. This is the outline of my presentation. First, I will address the requirements of body dust application and how they can be addressed by digital-based analog ICs. After, I will present a new digital-based biomedical signal amplifier, BioDIGOTA. Post-layout simulation results and conclusions come after, showing the advantage of the new technique for smart dust applications. Body dust applications. Body dust is a new frontier in the biomedical electronics. As I show in this top picture here, body dust envisions a swarm of drinkable biosensor devices with dimension comparable to the blood cell, so it's able to be internalized in the human body so that to sense, acquire, and transmit body information of clinical interest. In this context, each IC device has an analog front end, as I show in this block diagram here, which is in charge of sensing the desired signal and transmit it outside of the body. As the first block of the analog front end, the bioamplifier is responsible for amplifying the input signal without inserting too much noise and match with the sensor interface. In this kind of system, especially for body dust application, two critical issues turn out to be real design challenges, such as low area, tens of micrometers square, and low power, sub-microwatt power. A typical set of specifications can be seen in this table below, where it is worth to highlight the noise, the area, and the power as a critical ones. Digital-based design trend. On the other hand, there has been a new trend of designing analog building blocks in a highly digital manner. It means to use only standard cell or logical gates to implement analog building blocks like DAC, ADC, oscillator, etc. As is shown in this plot below, a digital-like analog building block inherently takes the advantage of the CMOS scaling, reducing the total area and the power consumption, and naturally it turns out to ask ourselves whether we can design a bioamplifier in terms of digital means. In this context, throughout the next slide, I'm going to show that it's possible, and I will bring interesting results for you. Digital-based biomedical signal amplifier, BioDIGOTA. This schematic shows a simple implementation of a capacitive coupled instrumentation amplifier (CCAA), which is a mandatory building block within analog front-end interface, as I showed in the previous slide, where a low noise, fully differential digital biosignal Operational Transconductance Amplifier (BioDIGOTA) is used as a main building block. The implementation of this BioDIGOTA and its system simulation performance are the main results of this work. To understand how the BioDIGOTA works, it's worth to recap how the classical OTA behaves in the analog world. Having said that, we are all aware that the main goal of the OTA is to amplify the differential signal while rejecting the common mode 1. To do so, this classical differential pair structure here creates a kind of virtual ground for differential input signal through this current mirror here, while not created for the common mode signal. The net value of the output current here is the sum of small signal current generated by the differential input, while nothing is seen for the common mode input signal. Based on the previous reasoning present in the previous slide, we could wonder if we could replicate this reasoning in the digital way. The answer for this is yes, and I will show in the next slide. To implement the same behavior of the OTA but in this time in a digital way, we can start with two buffers to sense the analog input signal Vn plus and Vn minus. When Vn plus is larger than the above 3 point Vt and Vn minus lower than the Vt, as you can see in this slide, we can adopt as output state two 3-state inverters to charge and discharge the voltage of the output capacitor according to the desired voltage polarity. In the case that Vn plus is lower than Vt and Vn minus is larger than Vt, the charge and discharge polarity is then reversed, preserve the OTA signal. Note that for both cases the differential signal is being amplified. When both input signals are either above or below the Vt, the common mode input signal is not transferred to the output to keep both 3-state inverter in high impedance mode. However, the common mode input signal must be fixed, and the question is, how could we do that? Before to understand how the common mode input signal is fixed, a little change must be done in the buffer topology to make it possible. Now, instead of using two cascade inverters to build a static buffer, we have to change the first inverter by a Muller-C gate, adding a new input in the signal path. You can see from this table on the right that the Muller-C based buffer only changes its output when the logic levels are equal, otherwise high impedance mode is triggered. Knowing that, in the last year, a very interesting idea has been proposed using Muller-C gate in which the input common mode signal could be tracked and cancelled through a self-oscillating threshold sample loop. Using this structure, we can charge or discharge the output node of Muller-C gate fixing the common mode signal. If you want to know more details about this implication, I strongly recommend this paper below. In the case of this slide here, when Vn plus and Vn minus are above the Vt, the output of Muller-C is discharged. Otherwise, it is discharged. As a conclusion, the common mode input signal is fixed as similar as done in the analog version. Since we are working with a fully differential topology, a natural question would be, what about the output common mode signal? As you may know, it also should be tracked and fixed. For this situation, two more buffers are added to sense the output nodes and the same logic approach is performed. If the Vout plus and Vout minus is larger than Vt, both outputs are discharged. Otherwise, they are charged. In this way, we can end up with a fully differential BioDIGOTA through table where each digital output signal can be generated and provided by each individual kernel map, as you can see here. This picture shows the bioamplifier uses BioDIGOTA as a building block. Logic gates needed to implement are also shown. Some interesting features regarding the design of this DIGOTA amplifier can be highlighted. It is a fully differential version. It is compatible with digital design flow. Its first stage includes 100 Muller-C elements in parallel to reduce the shot and thermal noise. Once we have just used logical gates, the power supply of the design can be lower and the low voltage and low power design can be achieved. And it's also CMOS scaling friendly. Simulation results. All the simulation results have been acquired for the layout video of the proposed fully differential BioDIGOTA 180nm CMOS technology working under 300mV supply voltage. It can be realized that most of the area below to the main capacitor is filled by Muller-C. This is because of the noisy area trade-off mentioned before. In this layout view, we can see that total area is around 0.03 mm², where the most of the area is consumed by Muller-C input stage in order to achieve the noise performance requirement. Another interesting fact is the active area of the circuit is placed below to the main capacitor in order to save area. The transient response with noise from a signal input of 100 microvolt at 40 Hz is shown in this picture, where we can see the gain of 3 dB with a THD equal to 1.5%, consuming only 144 nanowatt has been achieved. The transfer function from differential input to output, supply voltage to output, common mode input to output can be seen in the top plot here, where a bandwidth of 270 Hz and a common mode rejection rate of 77 dB and a PSRR of 80 dB have been reached for the middle band frequencies. The noise power spectral density is also shown here. The proposed BioDIGOTA achieves an integrated noise of 3.1 microvolt RMS. The area and power breakdown can be seen in the top figures. Most of the power is burned in the logical part of the BioDIGOTA, while the multi elements consume most of the area to reduce the noise. Multi-color simulation has been also performed, showing the average gain of 28 dB and the average noise of about 2 microvolts RMS. When we compare the BioDIGOTA with recent published capacitive copper instrumentation amplifier, it can be seen that it reached the smallest area working the lowest VDD, keeping more or less the same noise performance. A common figure of merit used to confirm this is the power efficiency factor given by this expression here, which relates the noise performance with the power consumption. In this case, lower is better, and we can see that the bioamplifier achieves 0.2 noise efficient factor, reducing the total silicon area. Conclusions. An ultra-low voltage BioDIGOTA has been designed and verified by post-layout simulation. The proposed BioDIGOTA has achieved at VDD equal to 300 mV a power efficient factor of 0.2, 3.1 microvolts RMS of integrated noise. It consumed only 144 nanowatts, and the total area was 0.03 mm². Based on the proposed BioDIGOTA, digital-based approach shows a promising strategy to implement an analog interface for smart dust applications. Thank you very much. Thank you very much, and I'm open for questions.